Hello, welcome to the next mini lecture for process control. We've just done 3 mini lectures about Laplace transforms and revising those. Now we can use that technique for process control and see what it can do for us for analysing systems. So we're picking up with the material in the lecture notes. This is what's down as lecture 2, page 8. And this is the problem that Professor Costas was looking at with you when he finished his last lecture. So we have a continuous stir tank reactor. There's a flow in of a constant flow rate F, some concentration Ca0. There's the flow out, a constant flow rate F, and concentration Ca, which is equal to the concentration within the stir tank. And there's a reaction taking place such that species A is turning into species B with a reaction rate constant K. So that's what you were talking about, and Professor Costas derived this equation here, which is the differential equation, first order linear ordinary differential equation, which describes that problem, and made a note of the initial conditions for it. So how do we solve it? There's the time-dependent equation approach, which will involve differential equations and some solution of differential equations. Or there's the Laplace transform approach, and we've seen that once things are in the Laplace transform, they behave in some convenient manner, and one way they behave is that the output function is simply equal to the input function multiplied by what we call a transfer function. So we can characterize the system behavior in one expression, which is then simply multiplied by input to get the output function. So that's very convenient, so we'll see how that can be applied. So now we're going to work through this problem using the Laplace transform solution to see how that performs for us. This describes the problem. Concentration in the tank is changing with time. F is the flow rate, V is the tank volume, K is the reaction rate constant. And Ca0 is the concentration of the flow into the tank. So Ca0 and Ca are both functions of time. Initially, these are both 0, and of course V divided by F would be the residence time of the system, and so F over V is 1 over the residence time. We want to solve it using the Laplace transform approach, so we take Laplace transform of both sides, and we can take advantage of its properties where we can separate out the addition terms. So we take the Laplace transform of the differential, take out the constants, Laplace transform of Ca, take out the constant, Laplace transform of Ca0. Laplace transform for a differential, remember that, it's S times Cas minus the initial condition Ca0. And we've defined the Ca0 as being 0, and so that term is going to go to 0 in our example, plus Laplace transform of Ca is equal to Laplace transform of Ca0. So we can just tidy that up and take out the common factor of Cas, and there we have our expression of the differential equation. And now that can be reorganized, and what we're interested in particularly is how does the output respond to the input. And so it's sensible to group them like this. We've got the output response here, we've got the input response here, and then this is the equation that describes how they're related. So this is the transfer function. This is the input, sorry, that's the output, and that's the input. So we can see that within the lecture notes slides. That's what's shown here. On this schematic we have the input, we have the output, and we have the transfer function which describes the relationship. So the transfer function is derived from the physical and reaction characteristics of the system, and once we've described that mathematically, we can treat it as a black box. And there we have it. So we found our first transfer function, which can simply relate those inputs and outputs. That was looking for at one specific case, and in particular it had the initial condition that CA was 0 at the initial time. That won't always be the case, so we need to generalize this a little bit to make it applicable to real life situations which might have a wider variety of initial conditions. So we've got here the case of a first order linear ODE, and we've introduced something new called the deviation variable. So what is a first order linear ordinary differential equation? Well, first order means that this is the highest power of differential, dy by dt. Linear means that there are no terms which are raised to a power, so there's no y squared, there's no dy by dt squared, so it's linear. And it's an ordinary differential equation because it has the total derivatives, it's not a partial differential. So this will describe quite a wide variety of simple engineering problems, and so looking at this solution will elucidate all of those. At steady state, what's going to happen? Well, at steady state, this term will be equal to 0, and yt will be a constant, and ft will be a constant. So ft is now our input function, and yt is what we're tracking. So they'll both be constant at steady state, so we'll call it yss, that's the steady state value for the output y. Fss is the steady state value for the input f, and so that will be their relationship, yss equals kpfss. And we're going to analyse the problem by considering the variable as a deviation from steady state. So rather than considering the variable as yt, we're going to consider the deviation from steady state and how that changes with time. So it's no different in terms of how the system's behaving or what it's doing. It just means that we're characterising it by how much it's moved from a steady state value rather than by where it is compared to some other arbitrary reference point. So we're going to give the term y a dash just to indicate that this is the deviation variable. So the deviation variable y is going to be equal to yt minus yss. So that's the difference between the actual value of y and the steady state value of y. And likewise, we can say the same thing for the input f. The deviation of f from the steady state value is called f dash t. We can see already we can do something here. We've got yss, so we can substitute this steady state value of y in to here to get yt minus kpfss, which is going to help us. And we can also note that, well, if we take the differential of dy dash t, differentiate this term by dt, then we'll be differentiating dyt by dt minus dy steady state by dt, and that's a constant, so of course this equals just simply dy by dt. So these two terms are in fact equal to each other. So now we can do a conversion. We want to convert our differential equation into the deviation variable. We can start to do that. So we know that dy t by dt, that's here, we know that's equal to dy dash t by dt, so we can substitute that in. And we've got yt here, kp ft there, and so from both sides of the equation we're going to subtract steady state value of y, so we're subtracting the steady state value of y there, and then on this side we subtract the equivalent value kp ss, and so then we can take the kp factor out. And you can see now this can be simplified down so that yt minus steady state y is equal to the deviation variable y dash t, and kp multiplied by ft minus fss, the steady state value of f, is equal to kp times the deviation variable for f. So we've got the same equation as we had before, very nice, and this works only for linear equations, and so now we can solve it. And the nice thing is that now we know that the initial condition, if we're supposing that the system's at steady state to begin with, the initial condition is that y dash 0 is equal to 0. So that when we take the Laplace transform to solve this, when we do the differential term, the y dash 0 term is equal to 0. So then we can write the equation for the generic first order linear ODE. We've got the output divided by the input is equal to kp divided by tau s plus 1, and so again this is the transfer function we found for this class of problem. So that's following what's in the notes here. How do we use this? Well, this relates the output to the input, and so we'd have to consider what's happening to the input. And various things could be happening to the input. The input could have a decay, the input could start rising, and we know that we can express all of these different types of things with the appropriate Laplace transform. So we're going to consider the case for a unit step change at time equals 0 and see how that can be accommodated. So now with that we can find what the response of the system is by multiplying the transfer function by the input, and the input function for a unit step change is simply 1 over s. So now we have this s term that's appeared on the bottom, and that's what's accounting for the input for the unit step change input. So taking a look at that in our notes, we're looking at the response to a unit step function. We can write the response as the transfer function multiplied by the input function, and the input function for the unit step is 1 over s. Put that in, and here we have in the s space the response of the system. We want to find the inverse Laplace transform for that, and we can do that simply by a table. There's a standard solution which will accommodate this form, and so then we see that the deviation response is equal to kp times 1 minus exponential minus t over tau. And so we know that this solution is going to be applicable to any form of system which can be written with that first order linear ODE equation, and then the appropriate values can be found for kp and tau. So what does this look like? So if we're plotting the deviation response y dashed against time, so at time 0 deviation will be 0 because it's coming from a steady state previous steady state condition. But then there's a step change to the input, and so the system starts to respond to that. So it responds, it gets larger, and then as time increases, the e to the minus t term starts to dominate. That term starts to diminish to 0, and so the function is just left with the 1, and so it tends towards kp, 1 times kp, when t gets very large. So that characterizes our response for this simple system. It gradually increases and approaches the new steady state value. And we can see that at particular times, when t is equal to tau, then that's e to the minus 1, and so we know that at that point we'll be 63% of the way to our new steady state value. When t is equal to 2 tau, then this is e to the minus 2, and so then we know that we're going to be about 87% of the way to the new steady state value. So tau is the time constant, and the time constant describes the characteristic behavior, time behavior of the system. Kp, we call that the steady state gain, because that tells us how big the change in output is compared to the change in input. And so the new output after the new input has been applied, the steady state gain will characterize how big one is compared to the other. Now that's written in terms of tau and kp, but this response can be universalized. The equation we looked at can apply to lots of different systems, and so we can consider all of those on a simple plot, whereby we look at the ratio of the response to the gain, and we look at the ratio of the time to the time constant, and then we get a plot which tends towards 1, and where t over tau, when that's equal to 1, when it's equal to 2, that corresponds to 1 time constant response, 2 time constants response of 63 and 87% distances to the new steady state. So this is going to be true for any system that behaves in the way described by that basic equation at the beginning. So it's got a universal characteristic to it. So the lecture notes take a couple more examples of that where you can see it happening. This is what we're talking about: input response, output response. That's what the input is actually doing, but we've just looked at the deviation from initial steady state, and so that's the actual step that we're looking at. That's the type of system that we've characterized, and any system that could be written like that will have this transfer function and will have this response that we found here. There are 2 more examples here in the lecture notes, and I recommend that you pause the video and take a look at these just to work them through yourself. The first is the case of a tank with heating. So we've got the flow coming in, the flow coming out, and a heater within it. And then the system gets characterized by parameters including density, heat capacity, heat transfer area, heat transfer coefficient, and you can work out the energy balance on a system like that. And you'd end up with an equation like this. And what do we see? Well, this is of the same form as the generic equation we looked at previously, where Kp is equal to 1 and the time constant is equal to V rho Cp divided by UA. So that means that without even having to solve these equations, we know what the response is going to look like. We know already that the system's going to respond like this. This solution is applicable to it, and when it's written in these ratios, you can directly read off this. So when t over tau is equal to 2, that tells us what y dash over kp will be. We know what kp is, and so therefore we can find out what the actual response is at that point in time. And the same thing works for the tank without heating, but where the level is changing. So we have the input, which is simply a flow rate, and we have a height of liquid in the tank, and the higher the liquid is, the more quickly it's going to start flowing out of the hole, the orifice at the bottom, and that's related to the resistance of outlet flow. So again, it's another example of a system that you can write down as a linear first order ODE, and again you can look at this equation and you can relate it to the generic terms. Steady state gain is R, time constant is A times R. And once you've worked out those, again, you know that this solution is going to apply to it. You don't need to work out your own solution. You can find a generic universal characteristic and read values off that to actually see what your response is going to be for the system. So the slide in the notes here illustrates that again. The next mini lecture will just take a little bit more of a look at what the characteristics of these systems are before we move on to some more complicated systems. Thank you very much.